who are going to make today's presentation on sustainable, equitable ecosystem restoration, especially in the context of restoration strategies adopted to mitigate Mississippi River Delta plain. Now, I've had plenty of interactions with Khalil on the topic and what will what we want and what I could get was it is such a huge project that I won't take much time myself, but leave it to them, both Richard and Khalil, to have as much time as possible. But a brief introduction that Mr. Richard Rainey is a specialist marine scientist and oceanographer, is the Coastal Resources Administrator within the Executive Division of Coastal Protection Restoration Authority, which is a leading state agency for hurricane protection, flood control, ecosystem restoration, and other community resilience efforts for Louisiana. Now, I can, being an ex-government servant, I can imagine that he must have climbed a very steep hierarchical ladder to attain this position and must be having many other related responsibilities. He has been leading such campaigns in the past since 1992 and evaluating such projects, maybe even earlier, but whatever information I could get is this. His qualifications have a bias towards marine oceanography, marine sciences, chemistry, and I may perhaps the biological sciences also. And Rick, you are welcome to the group. We are all waiting to hear you. Now, coming to Khalil, it's very difficult to talk about a person who has been not only a colleague and a friend, but also like a brother ever since we met in 1980s at Calcutta. Though our subject domains were entirely different, I being a hard rock geologist and Khalil opted to go and pursue this loose sediments related marine sciences. But we had one commonality of taking up issues pertaining to the working conditions of geoscientists in the country. And in this particular mentor was none other than Mr. Krishnanunni, who most of the time guided us as to what to do and even control us to some extent. And that is one association we are both proud of. But after some time, after we left, of course, doing our own official assignments, later on, Khalil migrated to USA after several hassles which come in the way. But he was able to pursue his passion for this particular subject. And he has come to a level where he has a huge responsibility and a very, you can say, a prestigious assignment of along with his team, and they are carrying out this. He grew in the subject and carrying out this particular assignment, and about which we will hear in the next few minutes. And presently, as program director, he, along with his team, are responsible for execution of a high-cost, high-value adaptive management program. This includes implementation of SWAMP, an acronym which you will hear plenty of times in the next few minutes. Now, one thing I would like to share about Khalil. We have had a recent obsession with COVID-19. And though it is away from the present today's context, the topic, but I must share this with all of you, that Khalil's son, the second son, has been responsible for the lots of improvements in the Covishield vaccine, and which gave a lot of benefit to, say, our country and most part of the world. I thought it is not out of context to where we can shared some pride in our children's achievements and all. Over to you both, Mr. Richard, Rennie, let me call you Rick, and Khalil. Thank you.
Yes, thank you very much. This is Rick Rainey. It's an honor and a privilege for me to be here today to say a few words about my friend and my colleague, Mr. Syed Khalil, and about how his vision has helped reshape the approach that we are taking to wetland restoration in Louisiana. In the 1980s and the 1990s, when the coastal restoration program in Louisiana was young, most of the projects that were being built were small, and they were focused on changes in water flow and salinity to relieve the stress on marsh plants. Then in the 2000s, as a result of damage from several hurricanes and an enormous oil spill, the state of Louisiana refocused these efforts. Not only has wetland restoration been combined and linked with hurricane protection in new integrated coastal master plans, but the projects that are now being developed are much larger and are focused on moving sediment. Active projects such as marsh creation projects, which physically move sediment to build landforms, and also passive projects such as river diversions, which allow natural processes to move sediment and build land, have both consumed the majority of our recent restoration funding. Now, when Syed came to Louisiana 20 years ago, he saw the need for a sediment management plan to guide the wise and efficient use of the limited sediment for restoration. Over the past 2 decades, he has conceptualized, planned, and executed this sediment management plan to learn more about available sediment in Louisiana, where it is, what quality it is, and the impacts from borrow areas from dredging inshore versus offshore for restoration projects, and also how to minimize conflicts over competing uses of the seafloor from the oil and gas industry and green energy infrastructure. And he's also created numerous sediment management tools that help project managers make decisions about using the best sediment sources for projects. Syed was honored with the 2021 Robert L. Weigel Coastal Project Award from the American Shore and Beach Preservation Association for his work developing the Louisiana Sand Resources Database, also known as LASARD. Syed and I have worked together to develop and manage Louisiana's Adaptive Management Program, which has been used as a guide for other states and other programs around the Gulf of Mexico to assess the importance and the impacts and benefits of restoration activities, and also to guide future restoration decisions. Syed and I have also worked together to develop and implement the System-Wide Assessment and Monitoring Program, or SWAMP for short, in Louisiana, which provides programmatic monitoring data to support adaptive management and also to support making informed management decisions. Also, although some of these data collection efforts may seem separate and isolated to some people, Syed has continued to stress the importance of understanding how they are intertwined and how these different data types could be combined in a meaningful way to help us understand the complexity of CPRA's mission and also the collective benefits of our projects. And to share this information with a more broad audience, Syed has written numerous papers and has presented at conferences around the United States, around the world, so that others can learn from what we have done in Louisiana. In this way, others can take what Louisiana has learned and apply it to their particular situations. And I would also be remiss if I did not also mention the late Mr. Krishnanunni. Although I did not have the privilege to meet him, he was a friend of Syed's, and from what I understand, he was a brilliant geologist and a great visionary. To honor him, Syed's most recent publication in the winter of 2022 edition of the Journal of Shore and Beach was dedicated to his memory. So without taking any more of your time this morning or this evening, I will turn things over to Syed. And again, I thank you for allowing me to be here.
Great. Can you all hear me?
Yeah.
Okay, good. Again, thank you very much. Thanks, Bala and Rick, for the introduction. I really appreciate that. Well, I deserve it or not, but then you guys are better judge. So it's my honor and privilege to talk to such an august group of high caliber individuals and the best of the best in the field of geosciences in India. And many of them I had privilege to working with, and it feels like as if I'm reconnecting my past. Returning to my talk, what you see on the screen is a aerial photograph of our talk. We can say that that is a restoration of wetland which is degraded in the tag plane here. And I also, in this presentation, I tried to compress many talks. Actually, these are just to give you the context of all what we are talking about. The sediment management is a part of it, but what context it is, if I don't give it to you, maybe you all will not really appreciate the whole thing. What we are facing in coastal Louisiana is basically an eco-catastrophe, if you permit me to say that. The good news is that we have developed and we think that we have developed the scientific know-how and technical know-how to deal with the situation and also secure funding for it. Before I go in full presentation, I'd like to have two disclaimers. One is that my units may be messed up because here we use feet, miles, and all that stuff. And I try to do the metric one, but maybe in many slides you will not see that. So forgive me for that. And also you will find some references right there below that. So I try to use as much as the reference material as I could. So do you see the slide moving?
No.
No. That is the technical problem I'm having. I can't move the slides. Where is my secretary? That is the problem. Can you see the slide moving?
Yeah. No, the second
good.
one is good.
All right. Thank you. I got it.
It's working?
Yeah, thank you.
Okay.
This is my secretary who is helping me out. So yeah, before I proceed, I must pay my tribute to the great human being in whose honor and memory this lecture is being organized. As I said here, he was one of the finest human being and a noblest soul I befriended with Krishnanunni. And to me, he was very modest man, very humble, down to earth, at the same time extremely intelligent, and very practical, a great visionary, and as I always say, worth emulating. And I'm just, when I was trying to develop this talk, I was really imagining myself what he would have said to me in his slang Hindi. We used to talk to each other on that. So that's what I think me and Bhalla can imagine that. And also I understand that my talk with Mrs. Unni will be there today, hopefully. And my regards to her, and the Nitin could also join. I'm happy they could. So again, thanks again to all the seniors and friends who are in the webinar. Mr. Partha Sarthi, who was really very helpful in this, Dr. Naik, and Bhalla, of course. And here we have sediment management team, Rick Rainey, Beth Forrest, and Rocky Weger, as well as my secretary. I'm really thankful to her, Lauren Pushe, to help me with these technical problems I'm having with this. So the presentation today is what it will be is about the Mississippi Delta Plain, geological history, challenges and issues, and land loss and its causes, mitigation plan, what we have developed, and ecosystem restoration or sedimentology restoration. I will just try to clarify that a little bit. And sediment management holistic approach, which we have developed here, and the final thoughts about it. The thing is that there is one thing which we will be able to say here is that the whole this is the whole presentation, if you can summarize that, is a story of challenges and opportunity, and revolves around mainly three, but several natural disasters, but mainly three. Two of them are natural disasters, and one is the man-made. What happened in 1927, a great flood happened in Lower Mississippi River, and which really devastated the area. And result was that the levees were built. I will talk about the whole levees were built, and those levees called the disconnect between the river and the delta plain, and then the sediment deficiency actually resulted in land loss. And then again, it became what land loss does, what marshes does, as they act as a buffer. So then they were gone. So what happened then, with climate change and all that, impending climate change, hurricane intensities and hurricane frequency change. And in 2005, we have two hurricanes which devastated the whole area. So we administratively merged our restoration and flood protection together. Then we had this big plan. Then we didn't have funding, but then 2010, a oil spill happened, which got us some plenty money, quite a money from the criminal and civil penalties to BP Water. So this is the story around that, and that's how we develop. So I will be touching upon that. Again, this problem. Do you see my screen moving?
Yes, it looks good.
Looks good. I don't know which one is moving.
It says presentation today.
It says presentation today, and then it is, yes. Now I got it. Yes. This is having some problem with the laptop and all. So to reorient you in this, where we are talking about this North America, and
Now I can't hear you, Syed.
what is happening? This is the.
There we go. We're back.
Can you, okay. I'm so sorry for these glitches. You can hear me now, right?
Yes, we can hear you.
Okay, good. So this is the degraded delta we are talking about in North America, in the northern Gulf of Mexico. And if you see this slide, and if you see my cursor moving around on this is the Birchwood Delta mouth, and you can see it is jetting out. And these are the Berry Islands across the land and all around this Louisiana plain. And this is the marshes. You can see the fragility of the marshes here, how fragile they are. So then, putting in the context of the whole thing, this is the delta types of dominant processes. Rick, did you see my slide moving?
Yes, I'm on the delta types. Yes.
Delta types. Yes, sorry about this. I don't know what is happening with this. My computer is getting.
It may take a little time, so but it's moving. Don't worry.
Okay. Now I have two computers open here. So this is, you all know about it. I'm just putting in the context of this, that after Galway, the river-dominated delta in which Mississippi comes into here, like here you can see down the panel, the photograph of that, and the wave-dominant delta, San Francisco. and also the tide dominant delta. In between, you see the Ganges here. I put it just for the context. So these are on the basis of delta characteristic fluvial versus receding basin processes. The second is that major delta world of the world, out of 24 out of 33 major deltas, they are sinking. Is the statistically has worked on this quite extensively. And other one is that on the basis of relative vulnerability of the coastal deltas, how in the next 50 years, what will happen in drowning and erosion of coastal areas. And they decide, and they classified into extreme, where the more than 1 million population will be affected, and high and medium. So where Ganges Delta come as a high naturally, extreme, whereas Mississippi is high on that classification. So geological history of the formation of delta complexes is just, because you're all geologists, so I threw it in. It started by embayment, late Cretaceous period of 100 million years ago. And then modern day Mississippi Delta Plain evolved during the Holocene epoch, just say 8,500 to 7,000 years ago. And during that time, the natural shifting or evolution of the river's courses was going on with every 1,000 or 1,500 years. And then these delta complexes that consist of delta lobe and basins, marshes, barrier islands. So if you see this, the formation of Mississippi Deltaic Plain and major deltaic lobe from Salis Cypremont, the oldest one, to the Belize Delta, the latest one here, you can see. And how it happened, it is a good, one good slideshow I'm showing you. This is a thesis, master thesis by Rosenwig in Tulane University, and it shows how these lobes were developed over a period of time, from Salis Cypremont to Cocodrie to Test Delta to St. Bernard Delta, and St. Bernard to Lafourche Delta, and then Plaquemine Delta, the precursor to the modern or Belize Delta. So these, all the deltas, 7 lobes were developed, major 7 lobes were developed in that year. And if you care to see, these are the actually, and hold this thought for me, I will come back to you. These are the natural distributaries of those delta lobes during that period. And so coming to this, once they were formed, so then came the great flood of 1927, as I talked about. And then the engineering of river was followed, and which disconnected the estuaries from the river and of the wetlands, and there was interruption of the delta cycle and reduction in sediment supply. The land loss and anthropogenic causes I will discuss also, both natural and anthropogenic causes. So this is the great flood of 1927. Just to say that 500 people died, displaced were 700,000, destroyed home were 130,000, and the area inundated was much more, say 6.5 million hectares. So when we say 500 people, imagine in 1927, this area as it is, the population is sparse, and now, and then that time it is quite big. So you can see on the left panel, the whole area, inundated area. And the total value of loss that time was $1 billion, when the federal budget really exceeded of US exceeded $3 billion. So what happened then? Then again, back to his thesis, the red you see the levees, the 1,600 line, 1,600 kilometer, 1,000 miles of levees all around here. This is the Mississippi River. This is your Bosphorus Delta, and this is the Chaflaya River. And you see the reds are the levees, and the green dots you see, those are all the flood control structures that were built. So what happened then? So if you care to see the Mississippi River alluvial valley, you see on the left top inset, you can see the Mississippi River drainage basin where my cursor is, And then you can see this purple, which is depicted here in this panel, and which shows the levee from here to here, the lower Mississippi River. And where in this drainage basin, there are 38,000 dams in there. And all these control structure engineering on what they did, they reduced the sediment supply from 400 million metric tons in before 1900 to 145 million metric tons during 87 to 2006. This is a study by Bede and others of the two lines. So what this did, this levee did, we all know that how the river behave in the late stages, and these were the Mississippi historic course. And this was, and if you see the right panel, this is all straight jacketed into, this is the flow lines and low capacity there. So they straight jacketed the whole river. And that actually resulted in this. The extreme sediment starved system led to the land loss, because what happened? First thing happened is levees prevented sediment into the marshes, so no sediment in the marshes. Then less sediment supplied due to dams up river. Then what happened, because this has been straight jacketed, the whole sediment which were there flew out from the Bedford Delta to the ocean and lost in the ocean. And this is what we are trying to do, this 144 45 million metric ton or whatever volume is. Actually, there is some controversy about it, but it's still a huge volume of sediment is going. So we are trying to capture this and re-divert it in the marshes. And how we do it, that's what we are trying to do. It's not an easy things to do, but that's what we are trying to do. Coming back to the losses, that was not the only thing which contributed to the human causes for the land loss, which is one study says that 70% of the land loss in Louisiana is due to human intervention. And dams and levee has a major share, but at the same time, if you see these canals and all that, they're developed for civil works and for the oil and gas industry. These are on the right panel, if you see, these are all your sediment structures, flood control structures here. This, what you see is 1910 oil spill, and 5 million barrels flowed, and 11 people died and injured. You see in the left, the oil pelican, I just threw in this picture, and oil marshes. What these oil marshes do, they die because of oil pollution, and the capture, normally this vegetation, they capture and hold the sediment together, and that capacity is gone. So that is our problem when the oil spill happens, and that causes the loss of the land loss. Remaining 31% of land loss are natural causes, and you can see this left panel, the hurricane track since 1855. You see how many hurricanes. This is only here, which is near Louisiana. I have left other tracks, which is not concerning. So if you care to see behind it is the Florida Peninsula jutting out, and this is northern Gulf of Mexico, where I'm moving the cursor, and all these hurricanes are there. And one of those hurricanes, 2005, Katrina, hit New Orleans, and it was, the sustained speed was 201 kilometers per hour when it hit it. And you see this panel, how New Orleans was inundated. Other natural causes are sea level rise, which is 10 centimeters here in Grand Isle, one of the highest. And this is another annual rate of subsidence map we just developed it from swamp. I will talk about that. And we can see the difference. You see on the red here, Bedford Delta, it goes 34 millimeter a year, or even 40 millimeter per year. And then slowly it goes up when it go to when the Holocene is thinner, it reduces. So this is how we have developed this map. It took 4 years to develop this, because you have to use the new technology of RTK and GPS for elevation measurements. So just to give another example of the how land loss has 850 square meter was lost, square kilometer was lost in 4 years. It is the impact of these 4 hurricanes major. As I talked about, the Katrina and Rita hit in within matter of few days. It is August 29, is September 24, 2005, one in the west part of the state and one in the eastern part of the state. And then in 2008, Gustav went through this. This is Baton Rouge here in New Orleans. They went through this, and it was, and then I came here also. So these are the 4 major hurricanes which came within 3 years period. Gustav was more personal. If you see on this panel, the roof you can see here a little bit. That's my house, and we missed it by inches. 3 huge oak trees fell on that. But my friend Harry was not really lucky. He got his house split into 2. But anyway, so these are the 4 hurricanes. You can see how much hurricane can cause the wetland loss. So in totality, when you look at the Louisiana, this is the before levee and other major intervention of human intervention. And this was 25% more bigger than this, which is now in 2014 and now. So in less than 100 years, we lost about 5,000 square kilometers of the area. And the next 50 years, it is estimated that somewhere from 3,000 to 8,000 square kilometers will be lost or additional risk if we don't do something about it. And that is, I mean, this is the variation is due to the which scenario you opt for. So this is the situation we are in. This is again from Harry Roberts, Bloom and Roberts, their vision of coast, and this is the what coast to Louisiana coast looks like in year 2000, and this is what it will look like in 2001, and this is their estimate is about 10,500 to 13,000 square kilometers will be lost by year 21,000 if we do nothing. So now coming back to that why do we care really this and what we are doing? There are 2 things. Why do we care? Because Louisiana is home for nearly 2 million people. Half of the population lives on the coast. And it also provides billions of dollars worth of natural resources and services to the nation annually. And that's why it is called America's wetland. A bit more of statistics here. Energy, the oil and gas, now this wind farm and renewable energy and all that is 70 billion per year, and it gives a job of more than 250,000 jobs. Whereas maritime and ports, there are 5 major ports here, and you have the 35 billion a year revenue comes out of that, and more than again more than 250,000 jobs. Fisheries again 3 billion. Moreover, the whole Mississippi Delta Plain itself is worth $1.3 trillion natural capital if you take into account the ecosystem services which are being held here. And then finally, what it has 37% of all the coastal marshes and habitat in continental US wetlands, and 80% of the wetland loss is from Louisiana. So this is the situation. What we are doing about it, as I said, that as Rick also alluded to, that in early 80s and 90s, we were doing the mitigative plans on the scale were not very significant. But 2005 devastation what woke us up. And we know that business as usual is not going to be the option. So we have to do something. So the state actually merged ecosystem restoration agency was doing that, the DNR, and the protection measures, the levees and floodgates, into one, and Coastal Protection and Restoration Authority here, which came into existence. And then we were supposed to develop land. So CMP, that is Coastal Master Plan of 2007, was the first master plan which has integrated approach for protection and restoration. And we are supposed to, required by law, to update every 5 years. Now, every 6 years, they have changed it a little bit. So a bit more detail about 2017 master plan, latest master plan we are in. The next one will be out shortly in 2023. So what we decided finally that there are two decision drivers. Main decision driver for there are two. One is the reduce flood risk for the populace. We have to take care of population and people first. And then building and retaining land, which will act as a buffer between us and the onslaught of nature. So that is that. And if you look on the right side of the panel, these are the various allocation. $50 billion is the price tag for this. And half of this goes to risk reduction and half goes for restoration. And that restoration has different strategy like Barrier Island, like marsh creation, you see, and then ridge restoration, sediment diversion, and others. All these things are there. So we understood that the land loss is basically sediment loss, and that we have 124 ecosystem restoration projects to build and maintain, so that we can build and maintain 800 square miles or 2,100 square kilometer of land in the next 50 years. So this, what we understood, and that, okay, this is ecosystem restoration that we need to do, but then basically it is sedimentological restoration by sediment infusion we do it. So we calculated the long-term sediment need in the next 50 years will be around 11 to 20 billion cubic yard, or this is billion tons. I mean, I'm forgetting how much of the billion cubic meter it comes to. I'm sorry about that. Short-term sediment need next 10 to 15 years is 1 to 1.3 billion cubic yard, and near term is about 150 to 160 million cubic yard. So these are all our needs of the sediment, and you can see the quantities of sediment. And we have limited sediment resources. When I said limited, the sediment means the compatible sediment which are for the suitable for restoration are limited. So naturally, when it is limited resources, you have to have the management, and which I will talk about a little bit. So I sum up here the sustainable ecological restoration, one of the papers, which says building, maintenance, and dissolution of coastal landscape is primarily a mass balance between sediment input and accommodation space that is created due to various natural and anthropogenic causes. This is the nutshell what is happening here, and we are trying to correct the situation. So one of the landforms we are trying to build is those barrier islands. These barrier islands are nothing but a narrow strip of land, but it helps a lot in wave attenuation, in separating the Gulf from the estuaries. And also, you can imagine the high energy event like hurricane, nothing, but still it is a speed bump for them. And what we are doing here, if you look at this barrier island here is unique in the sense that we have the sand towards the Gulf side, and we have back barrier marshes as its backbone. So if you see my cursor, this dike was built so that we can pump in the mixed sediment here. I will talk about the mixed sediment in a minute, and the sand here in the front. So that is how we are building this. So what happens that when the storm comes, something like that, they roll over. The feature is called roll over. So we are trying to actually pumping sand by work with the nature, not we are trying to have the rocks to hold this thing together, because it is a dynamic situation. And one of the lessons which we learned that you do the static structure for the dynamic natural processes, and that is how you work with nature. And this is a soft approach, what we call that. So this is another barrier island, and that showcases how scale has bumped up. We have taken up 3 of barrier islands here, 1, 2, and 3. If you can see that purple colors, these are here, and the sand source is here in the ship shoal right here, which is about 45 kilometers from this end, 25 kilometers from this island Timberlayer, and about 15 kilometers from the Trinity Island. So all these are these distances. We have to haul the sediment from here to there, and this is a big sand body, called ship shoal. So what we are trying to do is the 400 acres of fill we are trying to fill to mimic the natural geomorphology. So we are trying to build the geomorph by this, and the ecosystem by putting the vegetation and all this. We hope that they will catch up with that. So what we are doing, we are having the beach on the 4.5 feet. I'm sorry, again, that it's about more than a meter high. We build it, and dune is which is followed by a dune which is 6 feet, like 2 meters or so, and the back very much less than a meter in the back. And then we did it with 8 million cubic feet of sand and 1 million cubic of mixed sediment. And I said borrow source is quite big, and that cost a lot of money, and it's 166 million price tag for this. This is another feature, that is marsh creation. So this is one of the biggest marsh creation we have taken so far. And if you care to look at the left upper panel, these are the dikes which you create from the digging the in situ material. And when these dikes are degraded later, and then this area is filled in by putting pipes. You can see there are small pipes here, here, here. And if you see the inside, this is how the pipe pushes the sediment in these areas. So the total volume of mixed sediments is about 13 million cubic yard, whereas the mass plan build is about 11.2 square kilometers. Sorry, the mix-up of the metric and English units. Period of construction is 3 years, and total cost is about $81 million for this. The third major strategy we have is to mimic what the Mississippi River was before we built the levees. And as I told you early on, to hold the thought about the natural distributary, this is what I was talking about. These natural distributary will filling the water and the sediment into the system. And you can see in the right column also, this is how it was then. But now we have to engineer that. And this is what we have engineered here with red. You see that we build the diversions on the, has already constructed red ones. The green ones are the proposed one, and this one are the yellow are the engineering and design phase. So this is a kind of long-term solution we are trying to do, because it takes years to build the land. So this is a long-term solution. We are working on that. The earlier two, which showed that is short-term and near-term solution to actually hold the line for some time. And then we are coming to this. So basically, sediment diversions are engineered crevasses, you can call it if you will. So then this is one of the diversions. You can see how it does. This is the river, and then this is the outfall. It goes in the marshes. And our calculation is that it will build 70 square kilometer of land in next 30 years. And then again, next 50 years, another 54 kilometer will be added. And the cost at this moment construction is about $2 billion. So all these things I told you for the context of that, what we have been doing. So where the sediment comes into picture, as I said, the land loss is a sediment loss. And sediment on that magnitude of scale, how much we need it, needs sediment management. And so to sediment management, as I will show you in a minute, is a different definition for different organization, different individual, different situation. So we tailor-made or custom-made the Louisiana sediment plan for our purposes. And this is what it is. So you have this, we have the sediment in OCS, outer continental shelf waters, state waters, coastal zone, over Mississippi River, Atchafalaya rivers, and all these are different, the sediment types. And it is a very, as I said, very broad and encompassing term. And but the main objective here is to manage sediment efficiently and cost effectively. Everybody agrees on that. So what we do in our plan is identify all the proven and potential sediment resources here, and makes informed management decision to environmentally effective. That is very important here, and economically feasible, because we don't have deep pocket to go on doing this restoration. And also lately, what we have done, it has become a tool to minimize the conflict in the multiple users of seabed. A lot of users are coming up for the seabed. So sediment to sediment management plan is this, and this is what our management plan is, looks like. A few patches, 9 patches here, and each one, believe me, took a long time to think about it and put it in the right place. So the heart of this sediment plan is regional sediment management. The regional sediment has different meaning, as I said, to different organizations. Even here in Army Corps of Engineers have different definition for that. But in our sense, we in Louisiana has adopted the core principle of treating sediment as a commodity to be managed regionally and holistically for efficient, cost-effective, and sustainable ecosystem restoration. That is our mission, and we are solely focused to that. For that, what we did, we developed the how to evaluate the sediment, and we developed the protocol of exploration. And as Bhalla and Rick said, it took us almost to reach here what we are trying to do now, almost 20 years, step by step, baby steps we took because of lack of funding most of the time. So we have this sediment evaluation and sediment management. So first thing is sediment evaluation we did. We developed a protocol for exploration of offshore sediment, and then again later on added fluvial sediment, and is updated in 2019. And this is the guideline which is on the website, our website. The link is here. And to talk about a little bit, this is the first tool developed for implementation of our plan. And it adapted mainly for sediment investigation and sedimentologically complex deltaic environment. And it is a general guideline for sediment searches for cost-effective, comprehensive, and systematic investigation. It is a phase approach, as you see from the color coded. These are the 5-phase approaches, and initially with a reconnaissance survey, geophysical survey, and geotechnical investigation, followed by detailed one and the cultural resources. But this is, though phase approach, but this is pretty flexible, and we can adjust it in the field. I don't have time to go in detail, but this is what one of my colleagues from Mangalore office wanted to I shared with him late Bakr Zahir, and this he was looking for something like this. So the second one is the Louisiana database LASARD, which Rick alluded to. This was developed with a very humble start in 2003. But when we came here, we saw that we have to have, actually, I'm just backing a little bit. When I came here, I was looking for a map which we developed myself, Randir Sen Gupta, Smith Bhattacharya, and others in marine geology of the Gopalpur area sediment distribution map, and also for EEG sediment distribution. I was looking something like that so that we can plan better, but there was nothing. So then we started from evaluation. Now, LASARD actually helped us put, it was a very humble start, and with the $40,000 as a seed money, which is now, and LASARD actually annual budget is 10 times of that. But that is how we started. And we have this conceptually, and this manages archives and maintains geological, geophysical, geotechnical, and all related data on sediment resource exploration on GIS platform. And also it archives the CPR's historic current projects, data collection through our monitoring programs and legacy data. And this is the standard operating procedure we developed in 2016. Then again, recently we again updated it. And this is the link also that can be used. And these are the various, I said now it is more than 3,000 data sets, means, I don't know, maybe 300,000 or more than that data of various data here, which are there, which is formatted and put in this database. Then from that LASARD, what we developed, we took out all the sedimentological and acoustic data to develop this map. And this is first we developed it in 2012 to as a resource to develop the coastal master plan, to develop that, to help that in resource. And this map, what it shows your 3 things, 4 things rather: sand, mixed sediments, sand is green, mixed sediment is magenta, and purple is fine, and blue is unknown. You can see a lot of blue here. And we are developing it every time. And we also estimated the volume, which is first order, of course, volume. And beside being helping in planning, this tool has become really a very important tool for enforcement of our coastal zone management programs, delineation of federal regulations, offshore sediment resource areas, and decision in removal or otherwise decommission pipelines, data gap analysis, habitat mapping, and as such, it is, as you can understand, living document and updated annually. And this is the link, if you can see that is there, which can be found. This map can be found with the report. So just before we go to other, I just wanted to touch upon the sediment types. For the sake of restoration, we simplified the whole sediment type. We cannot afford to have all the detailed sediment classification. We took this Shepherd and Lefort diagram and have 3 lines, like 2 lines, one as 70% sand, one as 30% sand. The more than 70 to 100% sand is the sand we classified it. The rest 30 to 70 we classified as mixed sediment, and rest we call it fines. And of course, depending on the data density and degree of confidence, we further divide in superficial, potentially inferred, and definitely unknown is there. So this is how we have the sediment type exclusive for restoration. We did it. So if you take in perspective all the 4 tools, what we did, we have the Delta Sand Search Model or protocol for exploration, which feeds into the data, feeds into the LASAD database. And from LASAD, we developed this map, sufficiently this map. Now it is no more superficial. We are also going below the surface as well. And then from there, this is the recent tool we developed for Louisiana Sediment Availability and Allocation Program for project managers. If you care to say this one, this is the project area, then he or she has an option to look for the distance where they want to have, what option they have of the sand sources or sediment sources. So that is helpful for them. The second component is sediment borrow area. Once you dig and delineate the sediment, you dig the borrow area, and then the borrow area is there. So we develop another program, and it's talking itself, we call it BAM, Borrow Area Monitoring and Management Program. And it looks at the evolution through time, infilling of the infilling rate of in the borrow area, slope stability, hypoxia. And these are all the regulation requirements which we look at that. And I'm not going in detail because of time. So the second is the adaptive management, the third component of adaptive management, which Rick talked about. This is an expansive program under which, if you see the adaptive management and system-wide assessment monitoring program is here, the sum, and with which we collect the data, we standardize it, we project performance, and then loop back to this. So here, LESAMP is, our plan is excellent example, adaptive manager adapted over a period of time. And adaptive management program has helped extensively in implementation of LESAMP because we could collect other data on the basis of this. So these are the few examples of the data collected under monitoring program, the LiDAR data with elevation, the size geophysical survey of almost 6,500 line miles here, then about 10,000 line miles of bathymetric surveys here offshore. And on basis of all these, we developed this operational sediment budget. What it is a surface change surface between 2 surfaces. One bathymetric surface of 1932, 1936, and the other was 1985, 86. And that shows the movement of the sediment during that period. And cool colors are the sediment accumulation and accretion, and the hard colors are the erosions. So that shows the sources and the sinks of that. The last is this policy and regulation and coordination with stakeholder. And this is what I never thought that we have to deal with this, but this has become almost my routine job to deal with this coordination because of the multiple uses of the thing. And this is the paper which Bhala alluded to, we just wrote about this. So just to give you an example of that again, this is the pipeline. You see the lines, these are all pipelines. You can imagine the pipelines in coastal Louisiana, and the dots are the infrastructure, oil and gas infrastructures. And this actually one of the uses of the seabed. Then you have wind farm coming. Then you have this oysters, and then aquaculture. Then all these things are coming. So we have to be cognizant of the fact that we share all the seabed, and all these things limit our access to the sediment resources. So that is an important thing to keep in mind, and that the sediment management plan help us to do that. So this is the last one, just to, I'm taking, so this is the combination of all the data which we have developed. We are trying to develop a conceptual geological model of entire coastal Louisiana, which is not possible at this moment. So we are taking smaller steps. So area 1 we have chosen because it is in the Bertaria Basin, it is the deltaic plain, and this is the Mississippi River here. So we have taken this area 1 to develop the concept. What that means, this is about 2,000 square miles or 5,000 square kilometers of the area. And this is a 3-year program, which is ongoing. And actually, I have to have that meeting after this about this. This is ongoing project we have. So we collect all the SWAM data. We collected the operational sediment data, and that is helping us to develop the model along with these acoustic data, this geological data. All this data we are meeting together to do this. This is what I told you, to hold your thoughts about the distributaries, historic distributaries. These are the distributaries where the sand and sediment and water came. And we are trying to follow those and develop those. And this is once we develop, we will develop in a block diagram. We also will develop the sediment inventories and block diagrams, so the sediment distribution, to help our engineers and planners to better plan for the sediment resources, because we will not be able to go, I can bet you that 45 or 50 miles all the time. We have money now, we are using it, but then there will be time when we have be very, very economical about this. So this is what we are trying to develop. Finally, to recap, major disasters have modulated the course of events during the last 100 years. Mississippi River has been managed for multiple roles: navigation, commerce first, then flood control, then now ecosystem restoration. We dig it for renewable sediment sources for ecosystem restoration. Long-term solution for ecosystem restoration, flood protection, and channel viability and stability, that is partial de-engineering, is a very challenge. Mitigation for land loss via ecosystem restoration of degrading ecosystem is complex and challenging. Adaptive management, as you know, is vital, and there is no precedent of such approach on this scale. Some of the monitoring data collection efforts may seem separate and isolated, but they are entwined, as I said that. It all depends on how smartly we combine this in a meaningful way. Sedimentological restoration is the system scale, is the solution. The sediment management is fundamental to restoration. Climate change.
Yeah, I'm attending a seminar presently.
Climate change will not only inundate the project areas, but access to sediment will be more challenging. So identifying long-term efficiency is important. This is very important to keep in mind. So the final thoughts, our integrated coastal plan is developed during various potential future environment scenarios. Restoration projects that are selected are ones that perform best in the range of possible future scenarios. Changes in hurricane frequency, intensity, and phenomena rapid intensification may increase the physical damage to coast and accelerate the land loss. As we know that this has happened recently as well. And accelerated wetland loss, which future will consequently increase the need for the sediment. So we use all this. Historically, we have not built a resilient structure in the face of these dynamic. So what we have done, we have had the rigid structures where all the processes and all that, they are dynamic. Even the impending climate change, we don't know how much it will be. So keeping in mind the dynamism of the natural system and unknown climate changes, we are better off by planning dynamic and flexible approach. So now the trend is to build with nature, as in Dutch they call it, and here we call it engineering with nature. And also, I was asked whether how it helps in Indian scenario. I don't know much about the Indian scenario, but one thing I say that ecosystem restoration is nothing like one size fits all. It is all depends upon what is the local situation. But I can assure you that many of the Aries element components and tools which we have talked about a little bit, and the broader approach may be applicable globally. Say beach restoration, it is common strategy, and that the compatibility and approach and methodology is common, and that we can talk about. Sediment management approach, I mean, as I said, it is tailor-made for Louisiana, but then various tools we develop, like the evaluation of the sediment, the protocol, the database we develop, the LSAB we develop, the map we develop, all these things actually can be useful in Indian scenario as well, but depending on what they want to achieve, what is the mission of that project. So adaptation of principles and building with nature, it also helps. And this, I think, is all. These are some references I used, and thank you very much.
Thank you very much, Dr. Khalil, for the excellent talk and a lot of innovative ideas. And I think this problem which you have been taken up, I think will be repeated many places across the world in many deltas which have been facing. I think you have shown the way how it can be restored. And of course, you have certain uncertainties in view of the climate change, because we don't know exactly what is likely to happen and how the impacts would be. But my compliments to you and your entire team for the marvelous work which you have done. Thank you. Thank you very much.
Thanks.
If there are any questions, you're most welcome to ask. Yeah, please go ahead. Pansam. Dr. Pan.
Thank you. It was very nice. I only have one small. Not a question really. When we look at the elephant in the room, that is the climate change context and how it is going to affect the intensity of hurricanes, etc. The AR6 also had some calculations on that, how it will increase. So you did mention about that it has to be a dynamic plan, but how that dynamicity or how that factor can be, which is an unknown actually, can be incorporated. And it is an important thing because in the context of the domain and the area.
So, well said. I mean, that is very important thing that we understand the dynamism of the processes. What we have done, for example, I will throw an example as maybe I talk fast in the one of the examples was Barrier Island. When we have developed the Barrier Islands, initially what we used to do is put the rocks around that, or if you remember, you have seen anywhere else, they have sea walls built in early 50s and 60s. They have built sea walls, and they have, so these are the static structure. And now what we are doing, we are trying to jump start the natural process by putting sediment there. So this is kind of dynamism we're talking about, and that is being prevalent. Resiliency comes with the fact that you have to, I mean, of course, then the question arises, how much sediment we have to do that? And then the sediment, not only sediment, how much deep pocket we have to do that. But this is how what we are trying to mitigate the situation. by using, what they call it, managing the coast by moving people, by elevating the structures, and at the same time, by not doing any hard structures, by putting some soft approach by sediment and all that. That is in our scenario I'm talking about. That's what we do. The other thing is that if you look at all the levees that has built the hard structure, that causes into this big trouble. So had it been like partially shielded areas, like you have some areas where vulnerable, you put the levee, some area will not, just let it go. Like that would have been, but now because it is so set for 100 years, it is very difficult to de-engineer it, and not only the scientific part of it, but also the social aspect of it comes into play. So these are some things that we have to think about, and there is a lot of thinking going on here, at least in our organization, about this sea level rise. What are the other scenarios? What are the subsidence rate? How long the inundation will be here? So that's how we are trying to develop that. Of course, we have not achieved a lot, but we are trying in that direction.
Thank you. Dr. Khalil, may I request you to stop sharing your presentation so that we can see all people?
Oh, stop sharing. I'm sorry. I am so.
Yeah.
I'm so sorry. I'm just.
No problem. No, Dr. Parsarthi.
I am.
Yeah. Mr. Khalil, thank you very much for the excellent talk. I have some basic questions. One is, what do you really mean by land loss? Land loss, you said, is equal to sediment loss. Is it the land lost because of submergence? But if I see the delta lobes which you shown, the Mississippi Delta appears to be a sort of a prograding delta rather than a submergent delta. So what exactly do you mean by land loss? Because you said 800 square kilometers of land lost. So kindly explain. Sorry for my lack of knowledge in this field.
I was never expecting you to be there at the midnight. But you are there. I could appreciate that very much. Yes, that's a very good question. What happens, the lobes were developed, and that time the sea level rise was much below 100, almost there. The deceleration of sea level rise, it was the same sea level rise at that time, and when the delta lobes were developed. What happened after that? And then these delta lobes actually formed the deltaic plain. What happened after that was that what feeds into deltaic plain is the avulsion of the switching of the river and feeding the sediment in all the delta lobes, and that's how it goes on. But what we did, we straight-jacketed the river into one between two levees for 1,600 kilometers. So now the river is not doing its natural part, that is the movement here and there, the distribution. So what it did, the natural flow we stopped. So we deprived this, disconnected the process by which it was feeding the wetland. So wetland was sediment deficient, and when sediment deficient they started drowning in place, and they are not getting the feed from the river. So, and the whole thing was going all the way, as I showed in one of the slides, all the way to the ocean. So that's why this is, and as I rightly said, it is drowning, it is sediment deficiency, it is, as I said, there are natural causes of that storms. They come and destroy the marshes, and when they destroy the marshes, they take away the sediment, and that is distributed. And this is how all the land loss occur. So, and of course, that 70% of that is man-made, as I said, canal digging, oil and gas productions, and all this stuff. I hope I answered your question. It's a whole big subject. I can send you the papers.
Yeah. Dr. Ramani?
Thank you very much, Dr. Naik. Dr. Syed Khalil, that was a wonderful presentation. a very new subject to me. Being involved in coal mining in Pennsylvania, I'm very much aware of the very much aware of the importance of the Mississippi, Missouri river system for transport. Perhaps aided the development of the country tremendously, coal from Pennsylvania going to the port in New Orleans.
New Orleans.
However, what is very interesting about your talk, sustainable development and sediments. You know, we produce so much mining product, but about 90% of it is crushed into sediments and thrown away, accumulating as huge mountains on the surface, somewhere along the line, causing huge landslides, killing tremendous amount of people. And you talked about borrowing sediments from lands, which is another disturbance of the existing land use. Sustainable development is a wonderful concept, and we have some probable potential uses here. Let me talk about one more topic that you can comment upon, and that has to do with this Mississippi, Missouri Delta. You know, it was only, I think, about 20 years ago when the whole thing was flooded all the way from Nebraska down to Mississippi. The entire place was flooded, and now it is running dry.
Yes.
And this is the effect of climate change within the last 30 years. And we are talking about river flow and sediment transport. And these are tremendous amount of climate change impact of, you know, we can't even imagine, could not have imagined 20 years ago that this will happen. So there is a tremendous amount of uncertainty there. I would like you to comment upon your long-term sediment management plan or land use plan under these uncertain conditions, and some certain conditions like mining that have to exist, where we produce so much sediments and dispose of them in such dangerous conditions.
I mean, I'll try my best. I will try my best. So this is one, is that you talk about the sediment. Of course, we have this problems of the sediment. What you will appreciate is that it is not the cost of the sediment, but it is the cost of the transportation of those sediments to the respective area, which is exorbitant. For example, I will tell you that we had this Illinois mud, which was very resilient, and they wanted to sell to us. But even if barging it from there to Mississippi River is so cost prohibitive that we gave up on that. The other thing which I talked about, the maximum distance of 45 kilometers. We are hauling the sand from ship shoal. That is not the land, that is a shoal, summer shoal in the outer continental shelf. And we take it from there and haul it because of the environmental concern. We cannot go to the land. So environmental concern prohibit that using. Not only it is cost prohibited, but also environmentally it will be a very big challenge for us to do that. So the other, and you are very right. Here in our Mississippi River itself, we dredge every year about 80 million cubic yard of sediment for navigation purposes, and we throw away most of that because of the federal regulations and because of the cost. So Army Corps doesn't have the cost to put it in the place where we want, and we don't have the permission to take it. So these are the things we are trying to solve, because they are almost throwing 25 million cubic yard of sediment just like that per year. So there are the things which are, of course, federally mandated and regulations and all that, that's apart. But about the climate change, you are very right. That is one of the points which I deleted later, myself and Rick were discussing. that under this low water which we have now, we can see all this water next to Mississippi is next to our office. So this is the situation. How will we ever operate the sediment diversions on this? This is where you are very right. It is very difficult to operate. But then there are places when Mississippi River is overflowing and we cannot operate the spillway because the oyster people, the fishermen, and the others will get mad at us, and the governor or others won't allow us to do it because of political reason. So there are many things in play. As I said, had this been not levied, the societal issue would not have arrived. Now, de-engineering we can do. One of my friends, I don't know whether you know, Dr. Roberts here, he says very easy. Syed, it's easy to do science here, but very difficult to do the stakeholder engagement. Very difficult because of regulations and all that stuff. So we are trying our best to have this scenario, and that's what we said. We are developing master plan, and I think you are here in US. We can chat about it a little bit more, and I can pick up your brain on that at times, so that how best we can use that. I don't know whether I answered your questions, but I will try my best if I forget something while I was talking.
Thank you, Dr. Khalil. Let me say a couple of things about. I have fond memories of Louisiana. I have been in one of the big mines there in every island in the salt mine. I've seen that beautiful country. I'm also reminded of Dr. M.B. Kumar, a classmate of Krishnanunni,
yes,
who was director of the geological survey of Louisiana, I guess. And so there are very fond memories of.
No, he was. Yeah, he died. M.N. Kumar died. You know that?
Yes, he was a classmate of Krishnanunni. I'm a classmate of Krishnanunni, and we have such fond memories. Thank you for so fondly remembering Krishnanunni, such a fine person.
Oh, very. Thank you. Thank you.
Dr. Pradeep?
Nice talking to you.
Yeah. Dr. Khalil, it was just a fantastic oration by you. We came to know about the sinking of the area, the submergence of the Missouri Delta. Now, as I understand from your strategy, you are borrowing some sediments and dumping it into the submerged area of the delta areas. Now, what is the class size? Because if it was sand, silt, and clay size in the hurricane-infested area, these sediments, they will tend to get eroded from the place where you're dumping them. And submarine landslides would really undo what you are trying to do. So how are you really managing it without the larger boulder-sized material?
If I understand you correctly, you are breaking up a little bit, unfortunately. If I understand, Mr. Pawar, about your question, that Mawar, yes, I know him. Sorry, I know him quite well. So what I understand is that you're talking about the sediment compatibility, is grain size compatibility?
No, not really sediment compatibility. What I'm concerned about is the submarine landslides. Now, you see, in the west of the Missouri area, what I see from your maps is really some submarine canyon type of area. And if we put sand over there, the submergence will not be nullified. In the west side, you've got a relatively shallow profile. So if you dump sand over there, the land will obviously.
I got it.
But along with it, what I expect is that there should be boulder-sized fragments which should be put so that they can fight away the hurricane effect. No,
No,
the
actually,
erosional effect of the hurricanes.
okay. Let's back up a little bit. What is ecosystem? Ecosystem consists of the marshes, the landforms, the marshes, and the barrier islands. That is the comprised ecosystem, and that is pretty shallow. What you saw is the edge of the burst foot delta is that there is no shelf, continental shelf. It goes into slope, and I think that's what you're alluding to. We are not going there. That's
That
what
is what
our
I'm
problem
concerned
is. That
about.
we are not going. Pardon me?
That is exactly what I'm concerned about, because
Oh,
the
no.
shelf
We are not
area
putting that.
is also getting eroded.
No.
Because of the
We are not
hurricanes.
going there. We are trying to hold the line. We know somebody. We have drawing the line near the coast area, which is very shallow, and where the marshes has been degraded and all. So what we are doing, we are pumping the mixed sediment, which consists of marshes, and then on which marsh develop, and then once you develop the marshes, then they can hold the sediment. And the barrier islands, what we do, we put sand in the front, and which is also very shallow, hardly 10 to 50. I mean, the water depth from the marshes to the barrier island that is offshore, it is not more than 6 to 7 feet. But beyond that, of course, off the barrier island in the offshore, there are gradients. So gradient is completely gentle there. So I got it, what you said, the submarine slides will be further down near the burst foot delta, end of the burst foot delta. And then that is not our concern. Our concern is what is near the shore in the coast, which is hardly 10, maximum of 10 feet deep. So that's why we put it in the sand, not the big boulders. Again, the big boulders and other things, they are not actually compatible with the nature. And that's what we are trying to build with nature. What was there, what the delta built over the period of time with the delta lobes, as we're talking about the delta lobes, the front end was the sediment and for the sand, and the back end was the mixed sediment where the marshes and the bays and then were developed. So this is how we are trying to work with nature. And the boulders, I got you.
Hurricanes
That
would not have
boulders
effect.
are not.
Sorry, sir. The hurricanes would not have effect in those areas.
That is what I showed you one of the slides, that 4 hurricanes in 3 years, they took away most of the sand and we lost about 850 kilometers.
About, sir.
So once you develop that area, that's what we are trying to do. If you have this terra firma of the sediment there, it happens because your area is degraded. Once you have the terra firma of the sediment, a geomorphic form, and you have vegetation over it, once it grows, then it becomes really solid to work there.
That could work, yes.
Yes.
Vegetation could work.
Yes.
Thank you, sir.
Thank you.
Thank you, Dr. Khalil. Dr. Parsarthi, you have a last word? You have to unmute.
Yeah. Tell me, sir.
No, you want to say anything? Your hand is raised.
Nothing particular. I can tell the vote of thanks. Some thanks,
yes,
Khalil,
yes,
and
yeah.
Well,
No.
I think it's my present duty to thank my friend Mr. Khalil and his colleague Mr. Rick Rain for an excellent talk. And this technology itself appears to be new to the Indian conditions. I don't know whether we can attempt anywhere in any of the deltas, Indian deltas. If we can do it successfully, that will be fine. And I informed Mr. Khalil that this entire lecture will be put in the website in the next couple of days. And people, I am going to give you a mailing ID also, email ID also. So people can still write questions, send questions to you, and you can reply. That will be recorded in the website. Now I thank Dr. Nayak for conducting today's lecture. This is the 6th in the series, and I thank him for taking time today and conducting this meeting today. I find some family members of Mr. Krishnanunni. I find his sister Madhavi. I don't see others. Others also might have joined. So I thank them for joining today's lecture. And my special thanks to our opening batsman of this series of lectures, Professor Venkatramani. So he spoke, he was the first speaker of this 6 lectures as such, and he made it a point to attend all the lectures. I thank him for this one. I thank all the members who have taken trouble in participating in this today's lecture, and I hope they have really benefited very much by his excellent talk. Thank you very much.
Thank you. Thank you. Thank you all.
Thank you all. Thank you.
Welcome.
Thank you.
Thank you very much.
Thank you. Thank you.
It's about 2 a.m. here in Sydney right now.
It's 10 o'clock here in the morning. So
yeah.
It's 8:30 over here in India.
Wonderful,
Right,
wonderful.
thank you very much.
Well, you all have a good night.
Yeah.
Good night, sir.
Thank you, sir.
I am here, Dakshi.
Dakshi is there, is it?
Yes, yes.
Oh, hello. Oh.
A bit late. Had trouble getting the link.
Yeah,
initially.
that's it.
That's good.
Good,
That's
good. Lata is there? Lata, no. Lata Kudyan, no.
No, I didn't see her.
I also.
I want to thank all of you for organizing this lecture series. I'm very grateful.
I think Mr. Unni deserves much more than this, what we are doing. Such a great person. Whatever we do, it is nothing compared to his stature.
Thank you, Dr. Khalil sir, for your wonderful lecture. I also thank Mr. Naik for having conducted this very nicely, and also thank Dr. Parsarthi and all the attendees who have made it a big success. Thank you very much, everyone.
Thank you. Bye-bye.
Thank you, Ramesh, for joining.
Hello, Ramesh. हाँ खलील
यस सर
बहुत अच्छा बहुत अभी सब लोग हैं इसमें
हाँ बल्ला साहब हाँ
मैं बाद में करता हूँ
after 2 decades perhaps yeah nice thank you
Right then.
So EVR?
Yeah. So I'll talk to you tomorrow. Let me go to bed.
अरे क्या अभी क्या सोओगे तुम अब जाओ सैर वैर करो अभी 2 तो बज गया
अभी 2 बज गए भाई
बल्ला साहब को नींद नहीं आती आजकल बल्ला साहब को नींद नहीं आती आजकल लगता है
अरे भैया तुम मुझे दिन में 10 बार सोने को मैं 10 बार सो जाता हूँ
रात को नहीं सोते
नहीं रात को भी सोता हूँ
बाकी सबको जगा के
अरे हम तो एक ही बार सोते हैं मगर लॉन्ग टाइम सोते हैं बस
हेलो रमेश अरे नहीं ईवीआर कैसा था ये
It was fine, I said. Good. I think he has sent me the slides earlier. I have gone through these things. Quite an informative one, yes.
भाई काम किया हुआ काम है ना थ्योरेटिकल नहीं है
वही तो
काम किया हुआ है
नहीं my worry is whether we can really attempt such things in India with politics, money, so many things are not.
We haven't got the Delta X submergence maps as yet, or do we?
I don't know.
No, I don't think such a work has been done.
Yeah, I mean,
Delta submergence has been mapped.
And with a lot of Scandinavia all over, I don't think in Indian conditions we can attempt any such projects.
नहीं, Indian conditions
प्रॉब्लम
means
ये है कि कंसिस्टेंसी नहीं, पॉलिसी कंसिस्टेंसी नहीं होती ना. With the change of regime, the very emphasis will change. That's all problem.
Policy consistency तो तब होगी once we have a basic groundwork done. Once we have the basic maps in which the delta X submergence has been mapped, only then we can proceed to the next stage.
Mawar Sahab, who will definitely do that map, that type of mapping? Which organization will do that?
That can best be done by the remote sensing divisions, GSI.
I doubt. I have my reservations. Okay, it can be done by.
इसी के फॉलो अप पे एक आपस में हम लोग एक वेबिनार करते हैं आफ्टर मंथ कि whether this can be done or whether this can be sent as a suggestion to GSI or other agency. That's all.
Certainly.
I
Let us do our attempts also on the satellite mapping if possible.
Yeah. I think we should start doing it humbly with a one delta and trying to replicate whatever he has done.
Yeah.
Not the calculation, sediment calculation, but the basic things, and then talk to the people concerned. Maybe ministries.
As has been shown by Dr. Khalil, we have seen the levees and the fans overlapping each other. If we can even do that, with the fans overlapping each other, half the work is done.
Yeah, I think with the availability of high resolution imagery nowadays, we can do it. We can do it, absolutely no problem. And we can also do change analysis comparing with that 30, 40 years back data.
Exactly.
Right then.
Right
okay.
Then.
Good night.
Okay. Good night.
Good night.
Good night.
Good night. Good night, ma'am.
Good night, ma'am.